At the lowest level of Kubernetes, the core building block of any application is the pod. But a pod is incredibly fragile. It can crash, run out of memory, or be evicted by the system in a shattering instant. When that happens, the pod is permanently gone. It has no internal mechanism to resurrect itself. If the atomic unit of your infrastructure is completely mortal, you cannot guarantee the continuous availability that an enterprise system requires. Kubernetes achieves zero-downtime resilience through a strict architectural hierarchy of controllers. This diagram shows the separation of state. At the base is the living runtime, which consumes hardware and can die. Above it sits the desired state metadata, an abstract set of instructions insulated from physical failure. To understand how Kubernetes executes enterprise change management, we have to construct this hierarchy from the ground up. Mastering this separation of state is the difference between memorizing terminal commands and actually comprehending how the system maintains order. A pod is a physical entity. It reserves actual CPU cycles and consumes real RAM on your servers. Because it's a living unit, it transitions through lifecycle states. This flowchart tracks the progression, starting at a healthy running status, diverting to a crash, and ending at termination. To prevent traffic hitting a dead end, an automated system continuously checks these vital signs. Kubernetes uses a liveness probe for this. It regularly pings the container to confirm the application hasn't locked up or frozen. Alongside that, a readiness probe verifies whether the container is fully booted and actually prepared to accept user traffic. These probes execute simple checks, like testing a TCP socket connection or sending an HTTP GET request to a specific endpoint. But these probes share a critical limitation. They can restart a failed container inside an existing pod. If a pod is evicted entirely from the cluster, the probes cannot replace it. Relying strictly on probes creates a single point of failure. Maintaining the exact volume of required instances demands a higher-level manager. That higher-level manager is the ReplicaSet, the solution to the evicted pod problem. Unlike a pod, a ReplicaSet consumes zero direct compute resources. It is pure informational metadata stored within the cluster. Its entire operational existence is dedicated to a single task, constantly reconciling the cluster's actual running state against a declared desired state. It tracks these units using a match label selector. The ReplicaSet casts a strict boundary over any pod bearing a specific tag, like tier frontend. Acting as an auditor, the ReplicaSet counts pods sharing that label. If the target is 3 and a pod is deleted leaving 2, the ReplicaSet detects the discrepancy. It references its pod template to synthesize a replacement, pushing the count back to 3. But this controller has a hard boundary. If your development team needs to update the underlying application code from version 1 to version 2, you encounter a problem. Updating the template inside the ReplicaSet does not retroactively apply those changes to the pods that are already running. A ReplicaSet excels at guaranteeing the quantity of instances, but it completely lacks the logic to safely manage application updates over time. To handle change, Kubernetes provides the ultimate layer of the hierarchy, the deployment. Many engineers assume a deployment manages pods directly, or that it reaches into a running container to inject a new code image. That is a false mental model. When you trigger a change, like executing a set image command, the deployment initiates a rolling update. The deployment leaves the original version 1 ReplicaSet exactly as it is. Instead, it creates an entirely new ReplicaSet for version 2. From there, it executes an inverse scaling process, instructing the original ReplicaSet to scale down, while telling the new ReplicaSet to scale up. Parameters like max surge and max unavailable dictate the mathematical pacing of this transition, controlling how many instances can be taken offline at once. This shift continues incrementally. The new fleet grows while the old shrinks, until the old version reaches 0. At every single stage of the rollout, a specific volume of units remains online to process incoming traffic. Zero-downtime updates are not achieved by altering living instances. They are achieved by shifting the metadata target from one container fleet to another. The rolling update is seamless, but Kubernetes also offers a more brutal native alternative, the recreate strategy. Under recreate, every single version 1 pod is explicitly terminated before a single version 2 pod is allowed to spawn. This guarantees downtime, but it is highly effective in development environments or on clusters where strict resource limitations prohibit running 2 versions simultaneously. As applications scale, teams often look for advanced traffic shaping methods like blue-green deployments, canary releases, and A/B testing. None of these advanced strategies are natively built into the standard Kubernetes deployment object. To execute partial traffic routing or split releases, you have to implement external tooling like Argo rollouts or Flagger into your cluster. Even with standard deployments, failure happens. If a newly deployed version 2 application instantly crashes upon release, the system must recover. The industry calls this a rollback. Mechanically, a rollback is indistinguishable from a rollout. The deployment simply repoints the active desired state back to the preserved version 1 replica set, initiating a reverse scaling process to restore the previous environment. True Kubernetes mastery requires letting go of container micromanagement. By trusting the architectural hierarchy, you allow the system to enforce the desired state on its own.